Hello everyone. My name is Tobias Rådeskog, and I have been working as a consultant for ChromaWay for about 6 months, give or take. I'm actually an electrical engineer by education, but I've mostly been working in IT stuff, mostly in the legal field. And at ChromaWay, I work with the RELL development and things that are close to the database system of the blockchain. So tonight I'm going to show you a simple example of a RELL application, the true basics so you can get up and running. And I'm going to do this by showing a simple example of banking. One popular thing with the blockchains is to have cryptocurrencies, so it's a very relevant example. What we need for a banking application example is to implement functions to open accounts in the bank, the digital bank we have, and also methods to transfer currency from one account to another. This is possible using very little RELL code, 30 lines or so, short lines. This would of course only include the actual RELL code, not any application or graphical interface you would use to communicate with the blockchain. And an important question is what RELL code actually does. And you could put it in the way that it defines the interface towards the blockchain from the end application programmer side. That is, it gives or defines the methods of which you communicate with the blockchain. So if you want to create a web application that stores and retrieves data from a Chromia blockchain network, then you would need to write an interface module for the Chromia system in RELL. And that interface module would define how and under which conditions you can store and retrieve data from the Chromia blockchain. Then you call the Chromia server from your application using a specific library with which you can format your calls. We will go into the subject of operations and queries, which are functions you communicate with the blockchain with. And an operation essentially alters the blockchain, and a query would get information from the blockchain. So this is how it looks. Your application would communicate. Your application would use a library called postchain client. Postchain is an old name for a Chromia node, I would say, yeah. And with this library, you format requests and call the RELL operations that run on a Chromia node. And to actually, in our examples, we only use a single node. But of course, in the real world, you would run multiple nodes that communicate with each other to fulfill the redundancy and verifiability of a blockchain network. Because if you only ask one node, it's just like querying a database. So you don't actually get any benefits of a blockchain except for perhaps signing and so on. Some basic structures in RELL interface modules, that is the RELL code. Yeah, so classes, they define the tables with which you can store data in a blockchain, and this includes a definition of the data types a table should contain. And in the simple banking example we go through here, there's only one class, and that class defines accounts. And that's the identity of the account holder and the amount of cash that's in the account. And account holder's name and the cryptographic public key that is associated with the account. So that's the only data structure we use for this example, an account. And a bit of repetition. So operations, they generally alter the contents of the blockchain database. And they do not return any information other than if the operation was successful or if it failed. So if I want to send money from account A to account B, did it succeed or not? That is the only return value you get from an operation. And in most cases, one would want that operations are cryptographically signed, because it's not preferable to let whomever change the information in the blockchain database, especially in the case of a bank. If anyone could change anything, that would mean anyone could steal any user's money, which we don't want. And in our simple banking example I'm going through now, we have two operations. There is one to open a bank account and the one operation to send the money from one account to another. Then we have the basic bank functionality. And here is the whole operation for opening an account. And you have the input arguments up here. So what account number you want to have in the bank, and the account holder's name, and also a cryptographic public key, which you have to generate using a library as well. And we want the request to be signed using, and it's signed actually by using the cryptographic private key, but that's never divulged to the server, so that's why it says public key. You can see that it has been signed by a private key by verifying that it's a public key that's coming in. And also in this bank we have account numbers between 1 and 999999. And if any of these fail, the operation won't go through. That's why it says require. And finally, if those go through, we create an account that is. Do you know why this says create account? What account is here? Do you remember what we did go through earlier? It says create account.
Create a post.
Yeah, exactly. Create a post of.
In the table account.
Yeah, in the table account. Exactly. That's what I wanted to count to. Thanks. So we have the input arguments up there. So account number should be just the input argument account number, account holder name, and this bank is generous, so we give everyone who opens an account 1,000 units of currency. That's how we put money into the system, and this can be interesting to mention if you actually had a method here of like if you required a proof of work to get money here, it would be a very crude cryptocurrency. And a little more advanced would be to send money. And for that operation, we need to know what account number the money is going to, and the amount of money we are going to send, and also the public key of the user trying to send it. And the first thing we do in this operation is to check so that the operation is signed by whomever has the right to send the money. That's very important, preventing theft. And then we read how much money is in the account we are trying to send the money from. And you see here from the accounts table, you identify an account by the public key and get the account balance out. And we also require that there is enough money in the account to send. And finally, we increase, by using the keyword update, we increase the amount of money in the destination account and subtract the same amount of money from the source account. And also there is in RELL the concept of queries, and their intention is to retrieve data from the blockchain database, and that could be a single record of data or a long list of data, any type of data like customer records, pictures of cats or whatever. And in our simple banking example here, we only have one query, and that is to retrieve the balance of a specific account. So the input value to that query is an account number, and it returns by identifying in the table of accounts the requested account number and returning the account balance of that account. And then we go to the application side for actually using this. There is a library called PostChain Client in node.js. And you would normally communicate with a PostChain or a Chromia server running on your own machine. So that's the address to that server, localhost your own machine on port 7740. And then comes the so-called blockchain RID, and that's just a code which identifies a specific blockchain. So if you had a lot of blockchain nodes, all of them would have the same RID to identify the blockchain. So that's a specific blockchain. That's an RID. And this const rest stuff is just it's just to create a data communication object. It's rather technical. And then you finally create the communication object called GTX, and you also input what functions or what operations and queries you want to be able to call from that one. Here it's open account, send money, and get balance. And down here now it's a bit cut off, but we also generate key pairs or identities for two bank users, user and user 2. So you get both a private and public key from this command, stored in user and user 2. Then we make a new transaction using the cryptographic data of the first user. We want to open an account with account number 1 and the name Anders Lundin, that's a Swedish TV host personality, and using the first user's public key. And then we sign that operation, and that has to be done with the user's private key. That is never divulged to that key is never divulged to the blockchain system. It's intended to be kept on the client computer. And finally, we post that and wait to see that an account has been created. And we do the same thing and with the cryptographic details of user 2, and open an account with account number 2 and the name Fredrik Reinfeldt, which is the former Swedish Prime Minister. And we post that and wait for that it's created. And then we make another transaction and send money from, here we make a new transaction from the first user, that is account 1. And then we send money from account 1 to account 2 and 333 units of currency. And we sign that with the account owner 1. And then we post that to the server, that command, post and wait confirmation. And then it's done. That should have altered the blockchain. Finally, we will check if the money transfer has gone through. And that is done by doing a query. And the query function get balance from account number 1 and the account number 2. And then we just print it out, the result on the console. So, and it can be mentioned here that it can take some time for a blockchain transaction to go through and be verifiable. So we query it several times to see if it has gone through or not. It can take a little bit of time. And yeah, the results are printed, and that's what I think you're going to be successful with tonight. Yeah, so this is the RELL development environment, which you're going to start later, and you first define the class I talked about, the data structure, and then the operations and the queries, and it's all in the same file. So yeah, it's this is it. And when you're written the code, you just push start node up here, and it seems like it started correctly because you got a stop node. And then I have the client code here in a JS file, which I will run in node.js. And it can be mentioned that in this test environment, the database is reset every time you stop the node and start it. So there's no data there that was in a previous run, but everything is deleted when you stop it. So I just run a node on my code bank client.js, and that's the code I did go through as client code. And yeah, here it's waiting, confirmed. So we started out with both accounts containing 1,000 units, and as you can see, now we only got 667 units on account 1 and 1333 units on account 2. So the transfer has occurred. That's it. Doesn't get more exciting than that.